Hello, everyone. Um, so, good morning, good afternoon, good evening, wherever you are. Um, I'm really happy to welcome Professor Ramesh here to this lecture. And first of all, on behalf of my W2S team, my co-convener Brajbhushan, the W2S team members, Puspendra, Sakti, Ajar, and others, I welcome all of you to this webinar series. So far it's going very well. Today is the 76th talk, and we are really proud, privileged to have Professor Ramesh. So I'm really excited, but maybe my voice is not so, does not show that excitement because of some virus in my body. But trust me, I am almost feeling like dancing, but I cannot dance because of some weakness.
Yeah.
So nevertheless, I'm really, again, very, very happy and express my sincere thanks to Professor Ramesh for kindly agreeing to join this W2S seminar, and all others who are here today. We are going to now hit about 100 participants, and I'm really happy to see this overwhelming response. We will continue. Oh, just Dr. Albert Ford is joining. That's great.
Oh,
Yes. So Albert is a very regular audience in this webinar series. I'm really happy. Good afternoon, Albert.
yeah, Professor Ferd, yeah. And Professor Clayman, thank you. Yeah.
Yes. Okay. So I think Professor Ramesh really does not need a formal introduction to the spintronics magnetism community. He's so well known, but nevertheless, there are a lot of young students. For their benefit, they should know who is our today's speaker. So I will just read very briefly about Professor Ramesh's biodata. Professor Ramesh is a full professor at the Department of Physics and Department of Material Science and Engineering in UC Berkeley, University of California in Berkeley. He is also associated to the Material Science Division of the Lawrence Berkeley National Laboratory in Berkeley. Professor Ramesh pursues key materials, physics, and technological problems in complex multifunctional oxides. Using conducting oxides, he solved the 3-year enigma of polarization fatigue in ferroelectrics. He pioneered research into manganites, coining the term colloidal magnetoresistance, famously known as CMR oxides. His work on multiferroics demonstrated electric field control of ferromagnetism, a critical step towards ultra-low power memory and logic elements. I think we must have read a lot of good papers from this area. His extensive publication on the synthesis in material physics of complex oxides are highly cited. I just checked in Google Scholar. He has more than 103,000 citations with a H factor of nearly 150. He's a fellow of APS, SSS, and MRS, an elected member of the US National Academy of Engineering, and a foreign member of the Royal Society of London, as well as the Indian National Science Academy. His awards include the Humboldt Senior Scientist Prize, the APS Adler Lectureship, and McGrady New Materials Prize. Okay, I request all of you to mute your microphone except Professor Ramesh. And then TMS Bardeen Prize and the IUPAP Magnetism Prize and the Neal Medal. He was recognized as a Thomson Reuters Citation Laureate in physics for his work on multiferroics. He has served as the founding director of the successful Department of Energy Sunshot Initiative in the Obama administration, envisaging and coordinating the R&D funding of the US solar program, spearheading the reduction in the cost of solar energy. He also served as the deputy director of Oak Ridge National Laboratory and the associate lab director at the LBNL. Most recently, he served on the Biden-Harris transition team for energy. So with this very brief introduction, I request Professor Ramesh to begin. There may be a lot of new audience. I like to mention that during the lecture, we usually don't take any questions. So if you have any questions, either you please raise hand or just write in the chat box. At the end of the lectures, we will take all the questions possibly one by one. So with this, now I hand over to you, Professor Ramesh, and yeah, kindly begin your lecture. Looking forward to your lecture. Thank you so much.
Thank you, Shubhankar. First, thank you everybody for being a little bit flexible on the time. I agreed to be one of the Meet the Experts for the 3M meeting, which is going on now in New Orleans. And for some other crazy reasons, I could not go to New Orleans. I'm still very scared to travel, by the way, because I've had pneumonia a couple of times in the past, so I'm really worried. And so they said, oh, it's at 6 o'clock in the morning today. That was this. I just got notified yesterday. And I thought it was going to be next week, but they just said it's during the conference. And so we had to push back by half an hour. Profuse thanks to Professor Ferrite and Professor Clayman for joining. These are heroes. You know, I should tell you a little story about Albert. Now, of course, he has a Nobel Prize. For us, he's like a big sensei. But, you know, when I was back at Oak Ridge, I created the Wigner Lectures, which I wanted the staff to see, how do Nobel Prize winners think about problems? You know, Albert gave just a spectacular talk. All the staff was saying, this is what we need to do. This is a lot of fun. This is one person, after winning the Nobel Prize, he's still so incredibly active. We are trying to write a review article on electric field control of magnetism. And bar none, he's the most active amongst all of us, Manuel Vives, myself, and Felix Casanova, Nanagune. But Professor Ferrite is my, you know, I would like to be like him, you know. So thank you very much, Albert, for joining us today. Same with Wolfgang. I've known him for maybe 25 years. We have some fantastic discussions about ferroelectrics and stuff. I'm so happy to see you all, you know. And of course, everybody, you know, just be safe, be healthy. Okay, with that, what I wanted to try to do is to paint a bigger picture and see if it works with you. So I want to go back to CMOS, semiconductor electronics, and put electric field control of magnetism into perspective. And as you will see, of course, I'm from Berkeley, Lawrence Berkeley NAB. This fellow is a very smart fellow. He used to be at Intel, but he stepped down saying, we need to speed up things. So he, myself, and 3 other people, we founded Kepler Computing. For those of you from Europe, you know Johannes Kepler. Johannes Kepler broke the China. You know, he questioned how the universe looked like. And so Kepler computing has been designed to question everything and see if there are totally different ways for computing. And I have to say, we're having a lot of fun. It's based on ferroelectrics. And I will give you some of the background as we go along. And it's been a lot of fun. We've been in existence for about 2.5, 3 years now, and we are VC funded, and we're funded at the $100 million level, but it's a blast. It's a lot of fun. And so Sashi and I, we have been collaborating for about 8 years now, first from Intel and now from Kepler. Okay, so I begin by acknowledging people who we work with, a lot of people, our LBL, Beyond Moore's Law team. The work with Intel, Ian Young's team has been very, very influential for us. And more recently, our work with Nanagune. Felix, we'll see some of the data from Felix at the end of my talk, and my Kepler co-founders. Of course, like all of us in academic environment, the support is very critical. We've been very fortunate to have DOE support, and I'll talk a little bit about that. Support from Intel, of course, and the Semiconductor Research Corporation JUMP program. Shubhankar, you can hear me well, correct?
Yes, absolutely fine.
Very good. Okay, all right. So acknowledge all of them. Of course, we work with a lot of people. Like I said, we are working with Professor Ferrite on this review article. It's been a fantastic pleasure. And so I said we're going to take a different approach. I'm going to start with a short video. One of my twin daughters, she's a design person. So I said, hey, I want to create this, you know, panoramic landscape. And so she and I worked on this. It says changing the world one atom at a time, but let me see if I can play this video. The point is, you want to look at from a global economics or techno-economics perspective. Bring it down to the systems level, which is AI machine learning in our case. Then say, what are the biggest problems? Energy efficient electronics is really one of them. But we don't stop there. We go from there to say, how does new materials discovery or new phenomena like colossal magnetoresistance or spin-orbit coupling that you see here? This is a simple hydrogen picture, but the spin-orbit coupling phenomena can be very powerful. How does one go from economics on one side all the way to spin-orbit physics? That's going to be the focus of the talk. So we now say, okay, let's open it up. I showed you a 30-second video. Let's open it up and start to look at each one of them separately. Now, if you look at the macro scale, what's happening? There's a huge revolution, a tsunami that's happening in the field of electronics, information more broadly. Okay. What this chart is showing you is actually data from people like Intel, 40 years of processor performance. But as you can see, this is beginning to peter out because of three different things happening almost about the same time. The first is slowing down of Moore's law. Nobody will say Moore's law is dead because it's a techno-economic law. But it's true that you don't have the doubling of the transistors every 18 months anymore. It's actually very difficult because people like TSMC are already at the 3-nanometer node. Intel is getting very close to that. So how does one go into those kinds of length scales? So that's one issue. At the same time, the energy consumption in all of these electronics has not come down. And indeed, it's in some cases has gone up. And so people make jokes about it. At the same time, if you look at the other end from the demand side, what the customer is asking for is people like Google are already trying out driverless vehicles. They can work, but it turns out that you have to use a significant amount of your energy source for computing. There are people who have done calculations. You can take a Tesla, which has an 18-20 kilowatt battery. You can convert it into a driverless vehicle, but a significant amount, maybe up to 70% of your battery could be used for computing. Because you're driving at 50 miles an hour, you want to know how many cars there are, or if there are human beings walking around on the road, you have to be able to compute that. And you can do it in the cloud, or you can do it on the car. But in either case, there's going to be some huge computing involved. And you need a lot of sources of information, LiDAR, radar, all kinds of information coming in. They all require computing. So one of the things that we realized when we formulated Kepler was that the next generation of applications is going to require huge amounts of computing. So the question that we asked was, can we build computers that are 100 times more energy efficient than the status quo? Okay, that's an important point. And it's not a trivial thing to do because you're building a system. Building something at that scale with 100x more energy efficiency is not a trivial matter. Okay, so that's one of the drivers. Now, you could go back and say, let's look at that energy a little bit more. And if you look at this chart, it seems like a schematic. It's almost, but it's actually based on data. And what we did was, this is way back in 2014-15 timeframe, we looked at all of the deployment of electronics and AI, machine learning, IoT. And if you do that, a lot of people believe that that's growing exponentially. That's something that we cannot stop because that's the demand side of the market saying, hey, I want all of these kinds of applications, especially AI, but IoT as well. So with that exponential deployment, if you don't do anything to today's electronics, 100 picojoules per logic operation, whether it's 100 or 50, really doesn't matter because of this exponential increase. So if you do nothing to it, you can see that about 25% of primary energy is going to go into electronics. And if you look at the Semiconductor Research Corporation, which is a big body, it's the companies like Intel and TSMC and Samsung, all of them involved in it, their decadal plan, and I was involved in it in all honest disclosure, their decadal plan is even more intense. They claim by 2040, the entire world's energy production could go into electronics. So it's a pretty intense deal. Keep in mind, this is primary energy. In today's language, that would be a nuclear power plant or a solar power plant, or God forbid, a coal plant. And therefore, this is a huge change in the energy consumption. And in today's numbers, we're about 5-6%, so it's not that big a deal. But when it goes to 25%, as a point of reference in the United States, buildings consume 38%, because it's very cold in the Northeast right now. You need a lot of heating and cooling in the summertime, of course. Transportation takes 25% of energy. Manufacturing is about 20-25%. China is a little bit different because they have more investment into manufacturing. But the key point is that, there's a huge change happening in the amount of energy consumed. For a long time, people did not register this. This has now become so important that the Department of Energy is now deeply involved in this in the US. I'm going to show you a little bit of data from that. Okay, then you say, okay, if you believe in that I want to reduce the energy consumption in electronics, let's look at where we are. And the next couple of slides are basically going to tell you the state of the art or what we can do right away. On the left side, it's basically a cartoon. Again, we don't need to get very deep into it. This basically shows what the fundamental physics is for, say, a CMOS channel. That's controlled by the Boltzmann distribution function, which is shown here in the top left. Okay, if you apply that to the current, that's the I, that's given by this equation. You solve it, you get a very simple equation. KT log 10 divided by the charge of the electron is 60 millivolts. This is known as the Boltzmann tyranny. Why? Because the Boltzmann distribution function imposes itself on the CMOS transistor. Okay, that 60 millivolt per decade is shown here in the blue curve. That's in the ideal case. In real transistors, it could be worse than 60. Typically, it's about 80 millivolts per decade. Okay. Therefore, if you want to make a switch out of it, you need 6 orders of magnitude change in the behavior, so you know what kind of voltage is needed. That automatically tells you that you're going to be limited somewhere in the 800 millivolt kind of range. And that's where CMOS is today. Now, one of the things, Saif Salahuddin, some of you know him, very smart fellow, he's a colleague of mine. He has been here for about 12 years. He came from Purdue. He had worked on something called negative capacitance in ferroelectrics. And by the way, for people in the ferroelectrics community, this is a very intense topic. There's half the community believes in it. The other half has very strong reactions to the notion of negative capacitance. I wasn't going to go into negative capacitance. If I had given the polar skyrmion talk, I was going to go into it, and we just picked this topic. Now, what Saif was saying is, if I put a ferroelectric gate in the channel or along with the insulator, I could create temporarily, I could create negative capacitance, and therefore I could reduce the slope. And indeed, this is actually from a figure that the person who reviewed our Nature Materials paper, that person wrote this. So in principle, you could go down to below 60 millivolts, maybe about 50 millivolts per decade by using this ferroelectric. So there's a lot of effort looking at hafnium zirconium oxide or other ferroelectrics, for example, to get the negative capacitance. The other pathway, which is something that many of us were involved in, around the world. Yoshi Takura, for example, he's done fantastic work. We were deep into colossal magnetoresistance. We indeed published one paper. We never pursued it. I thought that was not a good idea. You could start to think about using correlations or using these correlated systems where you have very strong interactions between the spin, charge, lattice, and the orbital degrees of freedom to create what you would call a metal insulator transition or an insulator metal transition, approximately the same idea, where you could get very sharp on-off kind of behavior. And this would look very much like an extreme case of a CMOS channel where you don't have an exponential dependence, but really a discontinuous dependence. But nobody has shown it at 100 millivolts. I'm going to get to the 100 millivolts in just about 5 minutes. Okay, so this is one pathway. But if you look at it more broadly, you have the CMOS channel on the left side. You could look at negative capacitance. There's definitely a pathway, and many people are working on this. But one of the questions in the past 5, 6, 7 years that people have been asking is, hey, why are we using just the Boltzmann distribution on the electron, which is just running around everywhere? Why can't we use orders, degrees of freedom? For example, ferromagnetism, where the degree of freedom is a spin degree of freedom. Okay, you break time reversal symmetry. Can we use that? Can we, for example, use the exchange interaction as an internal source of energy? so that I'm kind of cheating on the Boltzmann distribution function. You still have the Boltzmann distribution function, but exchange interaction gives you another energy scale. Similarly, in a ferroelectric, you could use the dipolar order or the charge degree of freedom. You could think about using ferroelasticity, where the phonons are the key order parameter, or ferrotoroidic materials, where you have both the spin and the charge. But the key thing that I want you to take away, especially for the students, is now, I mean, this is where that transition from the macro scale to the physics scale is slowly happening. If you look at the architecture of your computer, you have the logic, which is made by Intel or TSMC or something like that, logic on one side, and you have the memory sitting in a different location. And indeed, a big portion of the energy consumption is moving energy back, the information back and forth. So people like Professor Patterson or Professor Hennessy at Stanford, they're saying, hey, why do I need to do this? I can build it right on top of each other. If you're an architectural person, electrical engineering type person, you would say, I build them right on top of each other. There's quite a bit of work going on 3D architectures. But if you're a physics person or a materials person, you say, I could start to use the double well structure. For example, in a ferroelectric or a multiferroic, I could start to build logic into a memory device. So this is a big push that's happening now. How do you do logic in memory? I'm going to give you one example of that. There's likely several different kinds of examples where you can use this. Okay, so we're going to get slowly into the materials and the physics part of it as we go through the next few minutes. And again, by the way, this is I like to take simple pictures. This is a rudimentary analogy of quantum materials or correlated systems. If you look at simple uncorrelated electrons, these look like the fish running all over. On the other hand, if you think about correlated electrons or exchange interactions or dipolar interactions, where quantum mechanics plays a very strong role, you can think of these like the fish. These fish are interacting through the hydrodynamic interactions. Very subtle, but nevertheless, the school of fish go together. Birds fly similar this way. So these are called correlations. It can be very small correlations or could be very strong, like in the case of the metal insulator transitions. Okay. Now, we could start to say, hey, I can now go back to the atomic scale and start to design these kinds of phenomena. And we use perovskites because it's such a pervasive material system. That's the structure shown here on the left side. The green are the big A atoms, for example, bismuth. The blue is the smaller ion, for example, iron. And the reds are the oxygen framework, which is the building block. For example, in our case, oxygen could be fluorine for that matter. And then you can take these octahedral coordination, you can tilt it, you can twist it, you can stretch it, do many things. And each one of them leads to different phenomena. Therefore, you can go all the way from superconductivity, the cuprates being the spectacular example, to ferroelectrics or multiferroics. You can scan the entire spectrum. You can have correlated oxides like strontium iridate, where you have essentially topological behavior. And you will see one piece of data towards the end of my talk. So with that as a building block, you can go to the next level above and say, now I don't have to be limited by just the electronic charge and the Boltzmann distribution function. And we kind of make a joke out of it. We call this the wheel of fortune for choosing physical phenomena. And you can see there's a whole range of physical phenomena. I'm going to talk about this MISO in a little bit more in detail. It's something that we've been working on with our Intel colleagues for a while now. Professor Fert and Manuel Bibes are all involved in this as well. So one could start to think about bringing many degrees of freedom. But that's not as easy as I make it with a single slide. There's a lot of different things that happen. Okay, so getting back to these 4 degrees of freedom, the fundamental degrees of freedom, one could start to think about the logic switch as a mutation of the order parameter. Now, here is where we're going to talk about energy for the first time. If you look at an STT-RAM, and again, these are approximate numbers, don't take it uber seriously, but it gives you a feel for the orders of magnitude. And Sashi and I did these calculations when we wrote the MISO paper. Normal numbers, STT-RAM is of the order of 10 femtojoules. And maybe there are people who are doing it 1 femtojoule by tweaking it and stuff. SOT is something that we're going to get to towards the end of my talk today. Okay. Now, if you look at a ferroelectric for the right kinds of polarization values and the coercive voltage VC, or the applied voltage, you can get to 1 attojoule. Typically, if the polarization is about 10 microcoulombs per centimeter squared for a 10 by 10 nanometer device, if the VC is 100 millivolts, then you can get to 1 attojoule. So we're going to get to this 100 millivolt as a very important benchmark. Okay. Now, this is a very provocative piece which Sashi and I still continue to argue. The argument that these guys made, this was the Intel paper, and this is really very fascinating because the paper came not from the academic community, but it came from Intel. It was a Nature Physics paper. What they claimed was that the ratio of the switching to barrier energy is optimal for ferroelectricity. This lambda, which is this barrier, the Landau-Doppelwells barrier to the switching energy, is optimal. This is the lowest for ferroelectric. We'll come back to this later. Okay, so I'm going to give you an interim summary. In terms of quantum materials for memory and compute, there's a lot of questions. How to? If there is a few slides that you want to take away, this would be one of them. How do you switch the order parameter at 1 attojoule? That's clearly a big question. We're going to talk about this. How do you get the right combination of correlated materials? You have so many things. You have topological insulators, you have multiferroics, you have magnetism, ferroelectricity. How do you get them to kind of work with each other? How do you detect the state of a magnet, for example, with a readout voltage greater than 100 millivolts? Professor Flirt is furiously working on it. So are we. We collaborate with his group as well. How do you connect the missing transductions? All of these now order parameters going back and forth, which really means the susceptibility terms. How do you use the emergent quantum phenomena for interconnect, like a topological insulator? People have talked about it, but how do you actually make it happen at the 10 nanometer length scale? How do you induce non-reciprocity, which is a directionality to this? Create conductive interconnects that scales very well. How do you deal with the thermal issues? You don't want to have too much of heat, and therefore I squared R is something that we are going away. At the next higher level, how do you connect AI functions? Now looking into the technology side, how do you connect these functions with the emergent behavior? That we have not thought about. What are the emergent behavior that scale well with dimensions, i.e. what is Moore's law for quantum materials? We know what Moore's law for classical silicon-based system. How do you perform algebraic operations or higher level algebra, which we won't get to for sure. And how do you compute the stochastic fabric? Do I really need an order parameter like Professor Datta at Purdue is looking at? Can you do probabilistic computing with these kinds of magnetic or ferroelectric systems? Okay, that brings me to one of the themes we'll spend about 15 minutes on and then finish up. This MISO idea, I was just coming back to Berkeley, and then the Intel folks called me and said, hey, we saw one of your papers. We were very interested in working with you on it. And they said, we are trying to make a device called a magnetoelectric spin orbit coupled device. That device is shown here, and we want to use your multiferroic bismuth iron oxide for that. And at that time, we had barely shown that when you switch the polarization, the green arrow by 180, that the canted moment in the bismuth ferrite also switches. This by itself was very controversial. There's a whole bunch of people who said, no, I don't think that works. And we used to have furious arguments about it. Does it happen? Does it not happen? Now, John Heron, whose data you will see in a second, he said, yeah, it does seem to change the magnetism. And Jorge Iniguez, really smart theorist, he explained it for us as to how all of this works from the ab initio side. Now, if you look at the MISO device, the Intel construction was that you input a charge signal, a voltage signal, and you use a magnetoelectric to convert it to a spin signal. Then you do all of your logic operations in spin space. Then you read it out as a charge signal. And the reason you have to do that is it's always much more easier to read out a charge than reading a spin signal. So you need charge to spin, which is multiferroics. You need spin back to charge, which is something which uses the inverse spin Hall effect. I'm going to show you one piece of data. There's some dramatic progress that's happening in this space, and I'll show you that. Now, for the students in the audience, if you were in this field, you got to say, forget listening to Ramesh's talk. I want to go to the lab and do the work right away. There is a lot of challenges, a lot of opportunities. Charge to spin conversion at 100 millivolts. That 100 millivolt comes from the attojoule kind of number. We are at about factor of 5 away, and I'll show you some data from that. Spin to charge conversion at 100 millivolts, 2-3 years ago, it used to be very far away, 3 orders of magnitude. But there's some dramatic progress that's happening in the field. You know, Professor Furt can, I'm sure he's spoken about this. There's just some awesome work going on, a whole bunch of systems. I'll show you some data on that as well. I would think we are at the 1 millivolt range today, and we are not very far off from hitting the 100 millivolts, but it is going to require quite a bit of innovation. Okay. Multiferroics, very quickly, you have seen the left side already. Those are the fundamental order parameters. Multiferroics are systems where you have coupling between these order parameters. So I can manipulate the magnetism with an electric field or the polarization order with a magnetic field. And I mentioned to you before, we will repeat it again, that the electric fields are typically a lot more energy intensive than a magnetic field, by a few orders of magnitude. So you're always better off manipulating the magnetism with an electric field. And again, this is a quick summary. It wasn't meant to be extensive. There are many pathways. And indeed, one of the things that would be nice to have is other pathways to make new multiferroics. Now, you could have A-site driven multiferroic where the ferroelectricity comes from the A-site. A good example is bismuth ferrite, bismuth manganite. You could have geometrically driven multiferroics like yttrium manganite. Lutetium ferrite is a good example. In these cases, the polarization is typically the dependent order parameter. So these are called improper ferroelectrics, but they also have antiferromagnetism built into it. You could have charge ordering, like a Verwey transition. These are not very robust materials. There's been a lot of debate in the community whether these are really multiferroic, how robust is the ferroelectric state there. This is the one where the ferroelectric and the magnetic state are very robust at room temperature. So not a big surprise that a lot of people are looking at bismuth iron oxide or chromium oxide. I mean, Wolfgang has done some spectacular work on that direction, and Christian Benek at Nebraska has done some beautiful work on that system as well. Now, Daryl Shlom and I have been looking at atomically designed superlattices where you can put a ferroelectric like lutetium ferrite and a ferrimagnet like lutetium iron oxide. And there's still a lot of work going on. It's not been fully resolved as to what leads to the coupling and stuff like that. But, you know, we published a really nice paper a few years ago on this, trying to say, hey, look, the epitaxy is the key coupling mechanism. Okay. For the next 10 minutes or so, we're going to focus on bismuth ferrite. This has really been heavily studied, and you'll see why in a second. It's got the perovskite structure that you see on the top left. It has a very high TC. And indeed, early days, the big argument was we published a paper where we said that the polarization is about 90 microcoulombs per centimeter squared, perhaps the highest polarization. A lot of people in the community said, that's crazy. And indeed, it turned out to be okay. Ab initio folks did clarify. We did a lot of other measurements. The reason was in the past, in the 60s and 70s, people were not able to make high quality materials. And with epitaxial synthesis, we were able to do that. Now, the magnetism here was really complicated. I'm not going to go into the huge drama that happened in the magnetism side, but this material has G-type antiferromagnetism, which you can see here. You have 111 sheets, which are ferromagnetic in plane, antiferromagnetic out of plane, like you see here. And there is also something more sophisticated, something called the Dzyaloshinski-Moria, or the antisymmetric spin coupling, S1 cross S2 kind of a term. That leads to a canting of the moment. And this canted moment actually is very important for coupling to another ferromagnet. It's only a small value of about 8 EMU per cc. Now, so the question that I think I mentioned this, that when you switch the polarization, this green arrow, by 180 degrees, what happens to this canted moment? Some of the original work said, nothing should happen. That's a symmetry operator. So the canted moment could be this way. Now, Jorge was saying, guys, that's not true because the polarization does not do the classical Vanderbilt switching. It doesn't go through the high symmetry state and then go to the other direction. Instead, the polarization is rotating very much like a ferromagnet. By the way, that by itself was very provocative, very troublesome for many people like myself who had been immersed both in ferroelectricity and magnetism. In magnetism, of course, the spin is unmutable, so you rotate the spins. But in ferroelectricity, we were taught that, hey, the dipole moment can mutate, and therefore it can reduce to zero and then switch. But BFO was behaving very much like a ferromagnet. Okay. But then with this work that we published back in 2014, it was now clear that indeed the canted moment was switching. And we use atomically precise synthesis, and many of you have this. Shubhankar has this system. Manuel Bibes at Thales has this as well. It's called laser MBE. We work very closely with Darrell Schlom at Cornell to do regular MBE. So we now have the power to synthesize these materials essentially at the atomic scale. And so the first experiment that we did back in, I went too fast, back in 2005-06 timeframe was to look at the ferroelectric domain structure of one of these films. This is actually pretty complicated. This image here is a piezo force microscopy image, and you can see contrast due to ferroelectric domains. You can take that to the synchrotron source and do something called photoemission electron microscopy. And what we see is that these domains, which map out the antiferromagnetic order, look very similar. So the question was, what happens when I switch the ferroelectricity? Indeed, when you switch the ferroelectricity, the domain structure changes and the antiferromagnetism changes too. So that paper outlined the fact that you can manipulate the antiferromagnetism with an electric field. Now, Michel Viret did a beautiful piece of work using neutrons, and he got the same conclusion. He used a single crystal and looked at the specific 2-to-2 reflection, and he showed that indeed when you switch the ferroelectric state, the magnetic state changes. Now, fast forwarding to 2014, this paper is the one that got Intel's attention. And so basically what we showed in this paper was that you take an lanthanum doped bismuth ferrite and put a spin valve on top of it, a very simple Coffey-copper-Coffey structure. And what we showed was when you switch the ferroelectric, shown in red, with an electric field, the spin valve resistance also changes. And we using Jorge's theory, we said, look, the canted moment in the BFO is switching back and forth, and we're manipulating that. And this is what got the Intel folks' interest. And this is the details of that. You can see that the GMR structure, the bottom layer is magnetically coupled to the LBFO, and therefore has a higher coercive field of about 120 oersteds, and the free layer, which is the top layer, has a lower coercive field, typically around 20 oersteds. And then when you apply an electric field minus 2.5, you see this GMR behavior. With plus 2.5, you can manipulate that. And so we showed that, hey, indeed, you can manipulate the magnetic state of the bottom layer. And this GMR was basically a readout mechanism. It's not what you would use for a real device. Our colleagues at Intel fabricated, 100 nanometer kind of devices. They all look essentially the same. The first challenge was how to go from 5 volts or 7 volts down to 100 millivolts. That's what Intel was asking for. So the first thing we did was to reduce the thickness. And this fellow who's now back at Bangalore as a professor, and Yenlin Huang, who's now back in Taiwan at Jiaotong as a professor, they worked very hard. And we were able to show that we can go from maybe 1 volt at 50 nanometer thickness to about 500 millivolts at about 20 nanometers. We also did some very rudimentary, and this is not meant to be robust. We used imaging, again, XMCD-based imaging, to show that 200 millivolts may be okay for a 10 nanometer, but not done in a very rigorous way. So this is still an opportunity. How does one do careful measurements at these kinds of scales? So this kind of is an intermediate summary. We now know that we can switch a ferromagnet room temperature with an electric potential of 500 millivolts. And this is the corresponding PEAM data showing that it's going from magnetized in one direction up to down. And the question is, how does one get below 100 millivolts? That's what Intel is asking for. And so we said, let's step away from this. And this, Sashi and I wrote a review for the Royal Society. This is both a challenge and a huge opportunity to go back and think about this. So here's your canonical structure. We can now make these ferroelectrics. These are all atomic positions. This is an atomic resolution image. So we can grow these with atomic scale precision with MBE or laser MBE. So this is a 5-6 unit cell BFO layer with metal electrodes. We can tune the Landau potential with chemical substitutions. So lanthanum does a very good job of that. So that's not a problem. I think we can tune it to a large extent. But one of the things that we didn't realize until we wrote that paper is that the Schottky barrier, strontium ruthenate, for example, forms a Schottky barrier. And therefore, you can have potential drops at the electrode ferroelectric interface. So we introduced a layer of LSMO into that material to manipulate the Schottky barrier. So that becomes important. That's something that we need to worry about, the electronic structure. Now, long time ago, 10 years ago, one of my students who is now a big professor at Tsinghua, Puyu showed that if I have an epitaxial interface between strontium ruthenate and BFO, depending on the termination of the strontium ruthenate, whether it's strontium oxide terminated or ruthenium oxide terminated, you could have different built-in potentials of the order of 0.6 volts, very large shifts in the potential because of just the termination. And the LAO-STO is a nice example of that as well. And another aspect that I'm going to show you one piece of data is something that the ferroelectrics community has never paid attention to, is what happens to these octahedral tilts, for example, or particularly what happens to mechanics. So this green box summarizes everything that we're thinking about. The VC total is what you as an electrical engineer are going to be saying, hey, I want to get to 100 millivolts. It's an equilibrium versus dynamic. There is a frequency dispersion to the coercive field. That's composed of the Landau component, which is here, the Schottky barriers, if you have any, the termination effects, the contact resistance of the metal contacts, lattice dynamics versus octahedral tilts. I will focus on this in the next slide because it's something that the ferroelectrics community has really not paid attention to. Okay, very quickly, this is our state of the art. By tuning the thickness and the chemical composition, we know we can get to bismuth ferrite with 200 millivolt coercive voltage. Very good hysteresis loops. Of course, these are epitaxial samples, but we know we can get good quality material. Now, a while ago, a few years ago, with Brian Huey, we looked at the thickness scaling, and this is just a quick aside. You can use now the atomic force microscope not only to look at the coercive voltage on a local region, but you can also shave it, atomically shave it. That's what he did. Use the AFM tip to shave layers and then measure the coercive field as a function of thickness. That's shown here, and this is the so-called K-Dunn law. It actually scales quite closely to the K-Dunn law. The thickness is T, it scales as T power minus 2/3. And we need to get to this green area. You can see that there are some samples in our collection, the 20 nanometer sample, which is reasonably close. But we still have some work to do in terms of optimizing our materials function. Now, there's one thing I mentioned that the community has not paid attention to, which has to do with mechanics. You know, if you look at the ferroelectrics field, the people who do piezoelectrics, they live in a different environment compared to the ferroelectrics field. So we take you through this piece of data. What you see here are domain structures. These are PFM images of a BFO layer, which is stuck to a substrate, and we call it clamped. And clamping I'm going to get to in a second. And you can see this very nice ferroelastic domain structure. If I simply lift off that BFO, exactly the same sample, lift it off, the domain structure dramatically changes. You don't have the stripes. There is no ferroelastic component. Instead, you see very nice 180-degree domains. If you measure the ferroelectric hysteresis, the coercive field comes down dramatically by about 35 to 40%. The blue is the freestanding, and the yellow or the orange is the clamped film. Now, we went back to our theory colleagues, both DFT and phase field, and I'll just show you the DFT data. What Jorge again showed was that if you look at BF4, it switches in these two steps, 109 out of plane and then an in plane 71 degrees. But if you look at this picture in C and D, what it's telling you is that when you have a film that's completely clamped and BF4 has this octahedral tilts about the 111 direction, when you clamp it, it takes a lot more energy. And you can see this dotted yellow line. That's when it's completely clamped for both the strain, the lattice deformation, as well as the octahedral tilts. And if you release them from the substrate, the blue is a release sample, that barrier can be about 42% smaller. The phase field calculations show exactly the same, but the difference in energy is about 60%. Okay. This is important because it's telling you that there could be big differences in the coercive voltage depending on mechanics playing a role. Now, mechanics also plays a role in the dynamics of the process. Here is calculations from phase field showing that a freestanding film will switch in about 1 to 2 picoseconds, while a clamped film will take 20 to 30 picoseconds, an order of magnitude. If I include the octahedral tilts, that becomes even more stronger. It goes all the way up to about 100 picoseconds. So we need to pay attention when we're looking at these structures, especially switching. You have a time-dependent strain that's happening in the ferroelectric because the lattice distortion is strongly coupled to the dipole order, unlike in a ferromagnet, which doesn't have that. Okay, and then of course we pursued quite a bit on looking at the switching dynamics. We now know that with very thin samples, small structures, these are 100 nanometer kind of structures, we can get down to about 60 picosecond switching. And for companies like Kepler, our goal is to get to 1 picosecond. We think it's possible to get down to 1 picosecond, but nobody's measured this. This data in green was measurement that I did back at Maryland 20 years ago in 2000. Where we use a photoconducting switch to measure the switching dynamics. So there's huge opportunities to understand switching dynamics at these kind of time scales. Okay, I think I've said enough about this. I will just say that Wolfgang knows a lot about this when we've had huge discussions about this. I just want to summarize this whole business. If you look at what happens during switching, the blue curve is a so-called Landau switching behavior. That is equilibrium, of course, and it's saying that you have to switch the dipoles coherently. In many cases, you don't have that. You have domain wall nucleation and growth, and you have something that looks like the green curve, which is what I call domain wall mediated, but quasi-static, meaning at very, very low frequencies. That barrier could be very different. While in reality, in many real applications, it's something that looks like the red curve, where it's still domain wall nucleation and growth limited, but it's in a very dynamic mode where it can be limited by the growth of the domain wall or by the nucleation of the domain wall. So understanding these differences is still very key. And we haven't done as a community enough measurements. There's some really beautiful theory papers. I'm citing 2 of them, Andy Rapp's papers, but I think we need to set up more measurements to do these dynamics really carefully. Okay, now I want to finish up in the next 5 minutes or so. We are now deep into the full MISO integration, courtesy of Intel. Felix and his group at Nanogune in Spain are leading this. And of course, Dimitri and Ian Young at Intel are kind of shepherding us. We are building these structures. We grew some of the samples and Intel people grew them as well. This is literally the first data. This has not been published. It's just been presented at IEDM. And you can see these are still epitaxial structures. We haven't gone to polycrystalline yet. Cobalt iron is our ferromagnet, and platinum is the SO part. It's the large spin orbit coupled metal. And we can indeed see switching of the inverse spin Hall effect. The magnitude is small because for these structures, coffee with platinum, that spin Hall efficiency is very small, maybe 0.1 to 0.2. But indeed, we can switch it back and forth with electric fields, showing you that you can do this work of creating the MISO. Another question is, how does one manipulate this to make it even better? And I want to finish up with just a couple of pieces of data. Professor Ferret has seen this data, but I wanted to quickly go through. Now, one of our hypotheses was that if you're going to be looking at things like bismuth selenide, telluride, it may be better to have an epitaxial interface. So let me take you through this data, and then we will finish up. So what you see here is lanthanum strontium manganite, which is an oxide ferromagnet. And on the other side, instead of platinum as the spin orbit metal, we use strontium iridate. Now, strontium iridate 113 behaves very much like a topological insulator. It has some very interesting electronic structure. It has band crossings in its electronic structure. So it has topological kind of behavior. It has iridium, so you have very large spin orbit coupling. So if you see the data here, this is a spin orbit torque efficiency, which is given by this rather complicated looking equation. Okay. It's as a function of the strontium iridate thickness. Now, if you look at the epitaxial structure, that's shown in red. And you can see as I make the iridate thinner and thinner, We think there are structural transitions going on and also electronic reconstruction going on at this interface. That efficiency can be as high as 1 to 1.5. On the other hand, if I use the same strontium iridate, but use permalloy as a ferromagnet, no interface epitaxy, you could see that that efficiency is of the order of 0.3. So these epitaxial interfaces can be dramatically different. We now have data from other systems which show essentially the same kind of behavior. Keep in mind, to get to the 100 millivolt Intel requirement requires the efficiency of about 50. So we are still far away, but we're not at 0.1 anymore. We can go to 1. We think we can get to as high as 10. And so here's a summary of the spin orbit torque. I apologize that I didn't go deep into it because the focus was on multiferroics, but there is work that's going on in our group and other groups around the world. Professor Furt is really the expert on this topic. We think we can get to values as high as 10. There are some oxide systems where we've already done the measurements. We're just verifying it with Dan, Ralph, and a whole bunch of people. We think getting to 10 is quite possible, this conversion efficiency. Getting to 50 is not impossible, but it's going to require some serious innovation. Innovating at the electronic structure level, because that really matters. You may have to play games with the band structure of the material. But this is now getting to be a very exciting direction for us. Okay. Let me skip this because this is just too much. I want to finish up with these summary slides. This has to do with convincing our colleagues at the Department of Energy that energy efficiency in electronics is important. It took us a while, but they have now gotten deep into it. They just literally 2 months ago launched a $60 million program, which is not large compared to the scale of the problem. But in this particular program, they funded 10 of the labs. And DOE has a very specific game plan that they follow. Our program is focused on 2 devices, the MISO device and then the NC-FET that Saif Salahuddin is leading. But there's a key difference here, which I wanted to point out, is typically, if you look at semiconductor, or for that matter, any product design, the people who are doing materials physics or process development or IC development, architecture, they all live in different buildings. In this program, we call it the co-design program. We all coexist together. All 10 of us are working together. For example, somebody like me on the materials discovery and synthesis, I'm sitting here looking at the energy landscape. How do I manipulate with Landau physics? Or can I change spin orbit coupling by manipulating electronic structure? But then I feed the outcomes of all of our measurements, the basic physics measurements, to my colleague who's building the junction physics for a single junction. Okay, using a code called Artemis, which is really a software package, where you can start to simulate using constitutive equations, a single junction. That then gets passed on to the device models people, which is looking at a 1 million atom ensemble, all the way to a single circuit. So this is another package, which is like a SPICE package. If you're an electrical engineer, you know SPICE as the bread, it's like the backbone for all of circuit simulations. But then we don't stop there. We then insert all of that learning back at the systems level, and that feedback comes back. That's why you see the infinity symbol here at the center. We keep going around back and forth into this co-design framework. Our framework is underpinned by the double well structure, which you see here in dotted lines. We are using ferroelectrics and ferromagnets, which is why you see the up and down polarization. And our goal, and this will be my last slide, our goal is to probe the limits of materials physics for logic and memory and NC-FETs with the goals of 100 millivolts or even lower, 10 picosecond operation, and 1 attojoule. We start with the co-design framework at the circuit and the device level, feed that information to the materials computation, the ab initio people who work within this materials project, which is an open database, where you can start to manipulate the energy landscapes and tune it very finely. Feed that information to the synthesis people like myself, and we make the materials with atomic scale control and feed it back to the characterization people at the atomic scale, imaging, spectroscopy, or synchrotron-based measurements, and this then gets fed back to our circuit design. And that's the so-called virtuous cycle, but it's a co-design framework. And with that, Shivankar, thank you very much once again. And again, thank you for being flexible with the time. I'm very happy to take questions on this topic.
Okay, thank you so much, Professor Ramesh. So on behalf of everyone, I really clap for your excellent lecture. I think it was like a medicine for my COVID situation. I could not really take my eyes off for a second. It was so nice, and okay, a lot of things you have put together, but that was expected as usual. I really enjoyed. Okay, before we take the question answers, I like to request all of you to switch on your camera, and Professor Ramesh, please stop sharing your screen.
Yes.
Okay, we'll take a group photo.
Okay.
Then we will take the question answer.
Very well.
Yeah.
Where's Professor Furt? There's Professor Furt.
You were just, okay. Hello.
Where's Wolfgang? Professor Kleiman.
I think he must be there. Okay, smile. Wolfgang, your video is off for some reason.
Yeah, you have to turn on the video.
Okay.
There he is.
Okay, I take more photos. A lot of people, more than 125 people actually. It was a record.
Hope it was worth the while. There I see my friend from Etaha. Marta is there. Morgana is there. Yeah, very good. Yeah.
Okay. So I think we took nice pics. Very nice. So we can take questions now. Thank you so much for your kind cooperation. I request you to switch off your camera. And I see already Astita Dubey. Yeah, please go ahead, ask your question. And Professor Ramesh, you may share your screen because you may have to use some slides.
Yes, okay. Indeed.
Yeah.
By the way, no professor, huh? Just Ramesh is okay, man. Just chill, no problem. Yeah. Hey, Priya, how are you? Hey, Asita.
Hello, hi.
Go ahead, Asita. Yeah.
First of all, thank you very much, Professor Vedanta, to provide this opportunity. I'm first time hearing Professor Ramesh, and I wanted to hear from a long time. The reason is that I'm PhD student and working on bismuth ferrite material, and it's really quite fascinating. But I would say I'm working with nanoparticles, not with thin film. And honestly speaking, it's like quite inspiring story of all these thin films and all. But I don't think so. I'm so intellectual enough to understand all the part, whatever you represented. But I have a fundamental question, could be stupid enough for you, that what's the Bohr atomic radius of bismuth ferrite? Like, I feel like if you make a film of 10, 20 nanometer, you are already working in quantum confinement effect. So you can really tune the band gap from it already, it's in visible range, like 2.3 or 2.2, something like that.
2.7, yeah.
2.7. So you see, you can go to IR, and which is like what quite demanding would be for photovoltaic people, because if you can have the band gap in IR, then you can have lots of solar.
Asita, so that's a great question. By the way, no question is dumb, okay? I think you're asking some fantastic questions. We actually looked at it very carefully, because if you look at the entire, this is before I went to DOE, when I ditched all of this stuff. If you look at the photovoltaics, I mean, essentially all of them use a PN junction to do charge splitting. We said, why can't you use a ferroelectric surface potential to split it? And it turns out it's a pretty large potential. And the efficiency is actually pretty high, but the quantum efficiency. The only problem is the carrier lifetime in bismuth ferrite is abysmally poor.
Yeah. Because
the D5 electronic structure is actually very stable. So even if you excite carriers, they immediately get trapped. The mean free path is like a few unit cells, couple of unit cells. So you don't get very large amounts of current, although you can get very large open circuit voltages. And so we showed, actually, one piece of work, we did a whole bunch of, it was just goofy research, nothing practical, I think. We had a whole bunch of domain walls, and it turns out that the open circuit voltage scaled with the number of domain walls. So you could get 15 volts open circuit voltage, but the short circuit current was really small. You need typically of the, if you look at silicon, it's about 50 to 100 milliamps per square. Oh, I'm mixing up my units, Astita. It's orders of magnitude smaller, mainly because the short circuit current is really small. And by the way, I don't know if you can think of, it's an insulator still. So the Bohr radius, I mean, we always think about for metals or something.
Yeah, because these all well-known, these halide perovskites or cadmium selenites, such kind of thing, they always talk about this Bohr atomic radius of.
Yeah. There you can do that because those are much smaller band gap than Bismuth. BFO is more on the other side. 2.7 is still pretty robust. I mean, it's a regular insulator.
Okay, thank you.
Sure, thank you. Yeah.
You want to
Priya, Priya had a question.
Yeah, Priya, please go ahead.
Yeah, hi Ramesh, very nice talk. I had, so you presented a lot of data, so I'm not sure whether I missed it, but you spoke of this, the clamped films and the, the freestanding ones, where domains, where your domains in the clamped one was 71 or 71 degree domain, whereas the other one was 180 degree domain. So we have an understanding why was the strain so large that the domain structure changed so much, or what is it?
I'm really glad. I mean, of course, I went through a little bit quickly because what I was trying to do is to sample a few universes, and depending on what people like, the reason it forms this structure, let's use the fancy pen. The reason it forms this structure, Priya, is because the spontaneous distortion in bismuth ferrite is very large. It's several percent, 7 or 8%. So it's a huge distortion. Again, that's because the polarization is huge, 90 microcoulomb per centimeter squared. So when you put it on a substrate, and this is grown on a dysprosium canted substrate. Now, dysprosium canted, you want to think of it as something like a rectangular substrate. In the sense, it's not like strontium titanate, which has got a 4-fold symmetry. This has got 2-fold symmetry. So what happens is, in this case, it forms these arrays of, these are basically 71 degree domain walls where the polarization is doing like this. I'm kind of drawing it in a very crude way, but each one of these bright stripes is a 71 degree domain rotated by 71 degrees away from the dark red stripes. Now, it's forming the stripe-like structure because of the elastic energy component, right? And so when I remove the elastic constraint imposed by the substrate, you're no more controlled by elastic energy. In this case, the elastic energy is essentially zero. It's a freestanding film. So the only thing that controls it is electrostatics, and it says, okay, I'm going to put an 180 degree domain in the structure. Does that make sense?
Kind of, but I mean, I was just wondering how much the angles, I mean, how much strain are you talking about here in this case?
Oh, I see. That's a good question. The mismatch strain between the substrate and the BFO is of the order of 0.7%. That's not huge.
Oh, I see. So even for such a small strain percentage, because of your shape of the unit cell, you're saying that it induces such a different behavior. Oh, very nice.
That's right. Yeah.
Thanks.
Sure.
Okay, I have a question. In one of your slides, you showed a GMR stack with cobalt iron, copper, cobalt iron, and it was also having LSMO. Here. So the two coercivities in the hysteresis loop are from the cobalt iron, or it is cobalt iron and LSMO?
Great question. I should have explained. All of this is from the copper Coffee stack. The LSMO is underneath the LBFO. And so LSMO is basically that, if you remember, I said, hey, one of the issues is the work function. Strontium ruthenate, turns out, which we didn't know until we did this whole piece of work, is forming a Schottky barrier to BFO. So we put LSMO just to manipulate the Schottky barrier. And it's sitting right on top. It's like a 2 to 3 unit cell of LSMO on top of the strontium ruthenate. But all of the magnetic stuff is happening here.
So then why these two cobalt iron layers are having different coercivities?
Great question. Again, I probably went through it very quickly. Thank you for asking me. The reason is this Coffee layer is exchange coupled to the LBFO. The LBFO is an antiferromagnet, a canted antiferromagnet. It's coupled, exchange coupled to the BFO. And that coupling is given by this coercive field. It's about 100, 120 oersteds, while the free layer is on the top. That's about 20 oersteds.
Okay, okay, thank you. There is a question by someone directly to me, so I'm reading it.
Yeah.
I would like to ask Professor Ramesh about his opinion about the prospect of magnetic skyrmions in low energy consumption electronic device.
Yeah, this is a great question. I mean, we should be asking Professor Ferd because he's doing some spectacular work on this. We are working as well. And I guess the key question is, now let me see if I can very quickly go back to one slide that I showed you in the beginning, just as a point of reference.
Let me just complete his question.
Yeah.
Then it says, for example, how about using ferroelectric control of magnetic skyrmions? How good is its prospect?
Yeah, a great question, by the way. I mean, so let's parse out your question into two parts. For it to become a real application, you need to do four things. You need to be able to sense the state. Is it an up state or a down state, for example? You need to have that state being very stable and retention, which if you're going to make non-volatile, for example, applications. You need to be able to switch the state very fast, maybe of the order of picoseconds. And for some of the logic stuff, you want to be switching even faster than picosecond. And then you want to be able to move information back and forth. You need interconnects. So those are the four things that we look for. Okay. Now the question is, at the next level, you also need to be able to scale things. If you remember, where was my? No, I went the wrong way. These two slides are really important because they are the criteria that you use to say, is this technology doable or not, right? It has to scale. So one of the questions for the magnetic skyrmions community is, and we are actually deep into this stuff in TMDs and those kinds of systems, what are the length scales? And if you look at the picture behind me, those are polar skyrmions. And the other talk that I thought I was going to give was on polar skyrmions, where the length scales of the order of 8 to 10 nanometers. But nevertheless, scaling of that object, the quasi-particle in this case now is a skyrmion. How does it scale? Can you make things which are smaller than, the 10 nanometer is like the state of the art today. If you want to do logic or memory, you need to get to those kinds of densities. So that's something to think about. Now, the whole business of electric field manipulation of these skyrmions, absolutely I agree. Professor Ferd is working on this. A whole bunch of people, Yoshi Takura is doing work on this. We ourselves are looking at, and we literally are looking at skyrmions in, for example, one of the TMDs. These are at room temperature, iron, cobalt, FCGT, iron, cobalt, germanium telluride. It's got a very high TC and it forms beautiful skyrmions. The question is, can you manipulate them with an electric field? Can you couple them to a multiferroic? The key point to keep in mind is this, and this is perhaps I didn't make a big deal out of this. The key point to keep in mind is, if you want to manipulate magnetism, it has to be with a field that breaks time reversal symmetry. The ferroelectric or the electric field does not do that. So there has to be a coupling mechanism. You can use electric field to manipulate anisotropy, but anisotropy has the same energy up or down, left or right. So if you want to switch something from left to right, up to down, you need to be able to break that symmetry carefully. So if you have a multiferroic, of course, you can do that. So if you can put one of these skyrmions, magnetic skyrmions, in contact with a multiferroic, you can do that. Now, copper selenide, for example, that Yoshi is working on, well, that's a good system because you can do that. So we are very interested, of course, in using these polar skyrmions. Maybe at some point we'll come back and talk about that, the polar skyrmions. But can you do doping of magnetic species? Can you put spins into them and manipulate them? Sujit, who is somewhere in the audience, and you just literally writing up this paper from Bangalore, on trying to see if I can manipulate individual spins, with the skyrmia. And indeed, you can do that, but you have to do it at very low temperature. So for a long-winded answer for a really important question.
Yeah, thank you. Amr El Sahid, please unmute and ask your question.
Amar.
Amar, you need to unmute. We're still. Yeah.
Okay.
Yeah,
Thank you for the lecture.
Yeah.
So I have a question here. I have noticed you usually use the PFO with a stripe domain structure for this kind of Beyond-CMOS electronics. So have you tried a monodomain PFO? Because
that's a great question, Amar. Yeah, great question. We haven't done extensive publications on it. Our work so far, we deliberately use the stripe structure because it's a reference frame. Those domains give you an internal reference frame with a length scale of 100 nanometers. In principle, we have done some measurements. Actually, Morgan, when he was here, he did those. He's never published those, or maybe he has, I don't know. Look, he has put magnetic dots of 100 nanometer kind of length scale within a single domain and looked at the switching of that. But we haven't done as much work as I would like to, yes, because we want to make sure that we understand it well enough. And the stripe domains, when Morgan and John Heron did that beautiful piece of work, they used the stripes to establish that indeed there's coupling, because you can use imaging techniques like photoemission, microscopy, to show that the ferromagnet is coupled to the multiferroic.
All right. Yeah. Thank you.
Yeah.
Thank you. Ramesh.
I can't ask question to myself. Ramesh Babu.
Ramesh Babu.
Yes, sir. Yeah. Thank you. Thank you for this opportunity. And I wanted to ask you a question regarding that electric field control of that spin valve structure, where actually this electric field is actually controlling the magnetization. Yeah.
Can you repeat again?
Yeah. So I mean to ask you a question in regarding to this spin valve control, where we are controlling the GMR. And here, are we controlling by the electric field? We are controlling the ferroelectric state of the LBFO.
That is correct.
And by means of the magneto-electric coupling, the magnetization is actually rotated in the bottom layer. And is that the changing the entire resistance of the system?
That is correct. Exactly. Yeah. So this layer is the most important layer because its magnetization direction is going from this to this.
Okay. And one more question here, that when you stated this strontium ruthenium oxide and LBFO, they actually form a Schottky barrier.
Yes.
Yeah. How is it confirmed actually? Because it's not like, we are having a metal and we are having, of course, basically if the metal work function is greater than the insulator or the semiconductor, then we call it as a Schottky barrier. And to manipulate this Schottky barrier, you have inserted LSMO, that to only two unit cells. 2 to 3
unit cells, that's correct.
Is that sufficient to change the work function of the entire strontium ruthenium oxide?
Yeah, you can actually see it in the symmetry of the hysteresis loop, Ramesh. So with strontium ruthenate, of course, when we use published values of the work function, it is larger, which I did not pay attention to for a while. It's about 5.1 EV, and though there is a band offset. You could also do, now we have done a lot of transport measurements, which shows that indeed it is a Schottky barrier. With LSMO, what we did was to simply put, different thicknesses. By the time you hit 3 unit cells, the symmetry of the hysteresis loop will start to change. No, there's a ferroelectric hysteresis loop.
Okay, yeah, thank you very much.
Sure.
Thank you, Ramesh. Probably we'll take the last question by Braj Bhushan. Braj, please unmute and ask.
Yeah, thank you, Professor Ramesh. Nice lecture. My question is related to your materials, because you are fabricating epitaxial, right?
Mm-hmm.
Yeah. But what about the polycrystalline nature? For example, why I'm asking this question, for example, topological insulators for bismuth selenide, people have thought initially, okay, if you have epitaxy, then you will have the surface state. But now we have also performed even inverse spin Hall effect measurement, polycrystalline bismuth selenide, found the highest value of spin to charge conversion by inverse Edelstein. Similarly, other groups are working using sputtering.
Right.
So my question is that because now this myth has been broken that okay, only you need an epitaxial topological insulator. But what about oxide if you do the polycrystalline case?
Yeah. By the way, fantastic question, Raj. For the ferroelectric, the polarization. Let's say take bismuth ferrite. The polarization is very strongly coupled to the lattice. And I think I made this point. This is why the mechanics is so important, unlike a ferromagnet, right? But so if I now take a grain and start to rotate it, you're going to have a spatial distribution of the polarization. And we already know that. For BFO or PZT, any of those ferroelectrics, when you have polycrystalline ensembles, the polarization becomes more distributed because it follows the lattice. Okay, so that's point number one. So you would think if the P, L, and M are coupled in the right-hand rule for BFO, the L and M are also going to change. So you're going to have a lot more complicated magnetism distribution in a polycrystalline sample, and which is why we have been doing all of our work in epitaxial samples, just because we wanted to understand the basic physics of this whole process. We were not even sure when we started this that the M would switch when I applied an electric field. Now we know that it does, and therefore we can go to the next step. So I think to make it manufacturable and all the other stuff, there are pathways to do epitaxial oxide on silicon. That we know how to do. We can even do it on 300 millimeter wafers. I even have 300 millimeter BFO epitaxial on a silicon wafer. But then you have to put all of the peripheral electronics, et cetera, et cetera. So that's a lot more complicated game. Now, people like Kepler Computing, my company, they're doing just a ferroelectrics part, but just by using polycrystalline BFO and stuff like that. So it's possible to do it, but it's a little bit more complicated.
Oh, thank you.
Okay, thank you. I think we are about time. I request you, Professor Ramesh, to stop sharing the screen. I like to share my screen.
Yes, please.
To present a small memento, online memento.
No worries.
Yeah, thank you.
For me, all of you guys joining is more than, I mean, Professor Fert is there and Professor Kleiman is there. So I'm already very happy. So thank you.
Do you see my screen?
Yes.
Okay, so it's a very small token of appreciation from our W2S team. I will read it for you. W2S Seminar Webinar Series on Spintronics, National Institute of Science Education and Research, Mysore, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Ramamoorthy Ramesh from UC Berkeley. In recognition and appreciation for being a very valuable speaker to give a lecture on electric field control of magnetism for Beyond-CMOS electronics. So thank you so much, Professor Ramesh. I really, from bottom of my heart.
Thank you for joining, guys. Yeah, made my day.
Yeah, thank you all for joining and be safe.
Everybody, especially our senior colleagues, Albert, Wolfgang, and everybody, just be careful. Maybe the end is not too far in the sense, maybe with this Omicron, we will get to the other side, but be careful, be safe.
Yeah, so please be careful and stay healthy. I'm currently infected, but better. I think Professor Ramesh's lecture helped like a medication today. So really, really nice. So next week we will meet again at 8 p.m. Indian time. Today was for some reason we shifted to 8:30.
Yeah.
So see you next week. And thank you so much and see you next time. Thank you so much, all of you. Ramesh.
All right. Be well. Bye-bye.
Yeah, thank you, Wolfgang. Bye-bye. Thank you all. Take care. Good night. Or have a nice day, either way. Bye.